Good afternoon. My name's Simon Davidman. I'm from Impirus Software. This is a joint paper between Impirus and Ultrasoc. And what we're going to talk about is some work we've been doing. But first, a little bit about Impirus. We are a simulation company. We're a 10-year company based in the UK, and our whole focus is building simulation and models, and we're a commercial company. We use a lot of open source. We make stuff available in the modeling under open source, but actually we're a business funded by customers and licensing our technology. Ultrasoc are a silicon IP vendor, and I've actually got a couple of slides on their technology, and they're presenting, I think, tomorrow about Trace, but this is a little bit about the debug side of things. And what I'm talking about is a collaboration that we've started with Ultrasoc to provide a good solution for a common debug methodology and environment between hardware-based with silicon and simulation-based for embedded software. So I'm going to talk about 4 or 5 different things, start talking a little bit about the embedded software challenges, which hopefully we should all know a bit about now. Then talk a little bit about traditional software debug, and obviously we've just had 2 presentations which are very much about developing debug using hardware. Then talk a little bit about what we can do with simulation, just a couple of slides on that. And then talk about how we're going to give better visibility in the hardware world and what we're doing to work together as this collaboration to provide a common development environment from working with simulation all the way through to hardware and silicon. So talk about embedded software. So software has been a challenge on processors forever, and it can be from simple things like the schedule, the quality, the reliability. But actually, more and more products are defined by software. Almost everything is defined by its software now. And there's new areas as well, new markets to do with deep learning, AI, and all of the challenges that brings. And also, at the other end, at the edges, all the Internet of Things. And these impact the software development process in terms of, I mean, you've got to have security in there, you've got to have safety in there. And there's all the challenges of how we can develop software in a predictable schedule, and to understand that one of the big challenges in software development is getting it delivered on time. If we take a look at a chip, this is a generic chip, just the type of things that people are building. You know, top left, we might have an SMP processor, which is running an OS like Linux. You might, in the bottom right, have something maybe a lockstep processor with 2 cores in it for some reason. Then there's going to be other bare metal, maybe there's other RTOSes and things in there. And then you've got, in any chip, you've also got all of the peripherals, the behavioral components in there, which obviously the software interacts with. And things are getting more and more complex. And it's not surprising that when the industry predicts and says what the cost is of software, it's getting worse and worse. And this is, I couldn't find a modern slide, this is an old slide I found, which basically is saying that the software is becoming absolutely the dominant cost in large designs. And of course, it's getting worse and worse. And multi-core obviously is having a big challenge and a big impact on that. But there's engineering schedules, there's everything. Software development is the thing that, you know, I know this is a RISC-V conference workshop, and we're talking about silicon and instruction sets and everything. But actually, it's getting the silicon in people's hands with software on it that actually is the thing that really matters. And the challenge of that is actually developing the software, I think. So let's talk a little bit about the software development environment. And as I said, we had two presentations already which have talked about it. And you know, we're a great believer in GDB and stuff. But the challenge comes, and it's interesting listening to Envercos talking about how with the GDB they're trying to address multi-core more than just multi-thread. The challenge is when you've got all these different components in the system, not just the processors of software, but also the behavioral components, how do you do it? And what people tend to do is have a GDB per core. Okay, if it's an SMP, you might be able to do it with threads, and maybe the new work in the upstream stuff maybe will allow you to talk to different behavioral components. But then you've got the issues not just with the GDBs, the simulation control, the controllers, the debug controllers, the thing which, as Jeremy says, start or stop the different processes and things. There's all of those things that have to be sorted. But one of the other challenges, and this is one of the things that is a real problem, is if you've got a GDB on a processor, the only thing you see is actually, it's almost like, in England we have letterboxes. I know in the US you don't tend to have that, but if you look through a letterbox, all you see is the street just outside your front door. But actually, what you've got is a whole floor plan of a city. You've got all these other things to see, and GDB gives you a very limited view. And one of the things you really need to do is be able to look at all the behavioral components in there as well. So you get little visibility outside the GDB. And one of the challenges with debugging on hardware is you get this lack of determinism and repeatability and poor control. You don't have the access into all the components to see what they're doing and to control what they're doing. And often, if you've got some complex bug of interaction between several components, how do you get them into that certain state to stimulate that bug? So hardware is a real challenging thing. It's hard enough when you've got one processor and some hardware. When you've got all of these complex systems with a lot of things going on, you have a pretty unmanageable problem. And that's the state of the art today with hardware debug. Whereas in a simulation-based approach, so we build simulators, and these simulators are instruction accurate. We model the processors. We have actually about 200 different processor models across all of the families from ARM, MIPS, all ARC across, and now the RISC-V. We joined RISC-V Foundation just over a year ago when we saw there was a lot more interest in getting software up and running, and we're a commercial vendor, and we saw the opportunity to provide commercial solutions. Because anyone who's developing a chip, there actually isn't an ISA that's been built that hasn't been supported by a commercial simulator out there. So our focus was to build a simulator for around the RISC-V solution, and this is an example of it. We build the processor models, but we have all the behavioral components as well. We have all Ethernet and USB and everything. And when Sci-Fi announced actually the original, I think it was an E51 booting Linux, I think it was, or U54. Originally, we built a model of that, and recently we built a model of the 540 to boot SMP Linux, and we have that up and running. And our simulator, one of the key things is it's very fast. And if I click the next button, hopefully you're going to see a simulation. It's actually a video I recorded of the boot of Linux. This is typing the left-hand side, the console. This is the simulator booting up. The simulated console's there. This is the Linux window. So that has got us to the boot prompt already. So it's under 10 seconds, depends on the processor. You log in as normal, and if you can type, you can actually get Linux commands to work. That's a typical problem. And then it shows you it's the 4 cores, and it's extremely fast and very efficient. We'll be showing it tonight if you want to look at it. This is just an example of fine. So it's from a software point of view, you don't realize that you've actually not got the hardware in there. So that was the 540, and as I showed, under 10 seconds to boot. It's very interactive. It actually models things like the Ethernet and the USB and everything. We can put that in there, so you can actually talk to the real world, the real hardware, plug in a memory stick and things like that. And we've simulated, actually for fun, we tried up to 4,000 cores just to see what would happen, little minium cores, just all running dry stones. And it's pretty slow, but it actually works and everything like that, so it can be done in there. So that's a bit about simulation, and it comes with full debug technology so that you can actually see what's going on. And we use an Eclipse-based, we have our own debugger, which is sort of, imagine it like, it's a bit like GDB on top of GDB, but what it allows you to do is you select which component you're interested in, and it switches the context, and you have a view on that, but actually it has control of everything else. So you click on a processor, you see all its registers in the software. You can click on a behavioral component and see all its registers, and actually the model there. So if you're debugging drivers, it's very, very good for that type of stuff, and you get complete visibility because it's a simulator. So that's a little bit about the challenge, a little bit about simulation. Now let's talk a little bit about hardware. So Ultrasoft is Assala, and what they produce is targeting in the embedded systems. They work with a variety of different vendors, so it doesn't matter really what you've got in terms of the processor, whether it's a standard processor or whether it's an ARM or whatever, or the RISC in there that you've got, RISC-V. And on top of that, or underneath it actually, they have a whole library of analytic modules. So these are components. This is silicon IP that sits next to the component and monitors and sees what's going on and analyzes some of the data in there. They have a fabric for message passing from these components that you've instanced in your device out, and then they have a set of communicators like JTAG, so you can actually get it out of the chip. And there are lots of different options, so they can actually monitor buses in there. They can actually get the data out, not just through JTAG, they can actually go through USB, so you can come straight out through the USB in the hardware. They've got a system memory buffer, so they can actually put a lot of information into that for storing. And they've got little modules that sit around all of the different components you might have in your chip. And it's silicon IP. You can put it into your silicon. And what it allows you to do is to monitor and control all of the different components in there to give you visibility and controllability into the hardware that's in there. We have a relationship with Ultrasoc. You should come and see Ultrasoc and listen to their presentations to actually get the sales pitch from Ultrasoc and see them this evening. But what we've been doing is working together. So the idea is that whether you're using simulation of your system or whether you're using the hardware which is enabled with Ultrasoc, the idea is that we have one common development environment so that you can develop your software and debug it and control it in a similar way from whether it's a simulator, which might be a year before you get silicon. It might be while you're still trying to add new instructions to see how the benefits of adding new instructions in there, all the way through to when you get the first RTL coming to life, pre-silicon, post-silicon prototypes, or even when it's in production, it can still be used to develop software. So this is a common development environment which is us working together to provide a common solution for our joint customers there. And it also gives us a few other things in there. For example, in a simulator, typically you don't see what's going on in the buses and things like that, but you can do. With the Ultrasoc technology, you have a lot more visibility into what's going on. And so the idea is it allows you to control your hardware or control your simulator in a similar way, get visibility into the software and how it's running, and trace information out into your debugger and analyzer. So you can actually get to control and debug and observe it through the design process. So way before you've got silicon, you can start playing with this and get an understanding of how your system's going to work, and then go all the way through to silicon. So in summary, we're producing this common development environment, so you get the same for whether it's hardware, RTL, or silicon, or simulation. And the idea is you can start early, without even any RTL written. You can use it with the RTL as the design progresses. When you've got prototypes, maybe in an FPGA, you can control it with this, and then when you come through to silicon. So, thank you very much.
In the connection between your Imperis MPD and the Ultrasoc, those channels, are those standard communications that you could plug in other IPs other than Ultrasoc IPs?
Yeah, what we've tried to do, the question is how they interface. We try and use standards when they're there, like RSP and MI and all these types of things. But when it comes to the multi-core, they're actually, in RSP, it doesn't handle the multi-core process yet. So we've actually extended that, and we'll make that public, what these extensions are. So it could be extended, because you need to target what you're controlling. And in working with Ultrasoc, we're working out exactly what was Imperis developed. We're having to share that, yes. So it will become standard, I hope.
So those communication protocols, I don't mean low-level communication transport protocols. I mean the actual debug protocols.
Yeah, what's in the Ultrasoc stuff, I don't really understand and know about. From the agent to us, that's what I was talking about, the RSP++.
Hi, thank you for your talk, by the way. In one of those pictures you were saying when you were showing the hardware with the SoC, you had a lot of peripherals with their own individual cores.
Yes.
I was wondering whether you do any cycle-accurate simulation of those individual peripheral cores as well as the big CPUs.
Yeah, okay, so cycle accurate. So the simulator is instruction accurate, so we do not model the cycles of the processor, but we have notional time, like any event-driven type of simulator or whatever. So we understand that things take time and everything, and we put a notional time to the instruction. So you say the frequency of the part. And when it comes to modeling the behavioral components, they understand real time. So we don't model the cycles in a behavioral component, but you say this is going to take 10, whatever it is, in femtoseconds or nanoseconds or whatever it's going to be. So we actually do model all timing, and then we simulate to the appropriate time. So the whole system has a notion of time, otherwise you wouldn't be able to interact with it and everything. And actually, it goes much further than that. We can actually talk to real devices, so we can lock it to real time, so that when in the simulation, we read and write to Ethernet, we can go to the web and actually download and install it as Debian and things like that is how we do it, talking to the real thing. So there is absolutely a notion of time in everything, and the simulator does handle that, but it's not sort of cycled like that. It's done by time. So as a user, it feels like the real thing, which is, and the software does not know it's not running on hardware. It should know. Okay, thank you.